Last time we introduced columns and buckling of columns in the context of a very idealized model, just to give you some idea that there are loads at which there are kind of threshold loads, we call them P critical, where if the load is less than P critical, you're in a stable regime of column bending or column deformation, and then if your load is greater than P critical, you're kind of in an unstable situation. Today we're going to make this more precise and really actually generate the equation that's actually used for column buckling. It's a very classic problem in applied math and engineering. So it does involve a little bit of math that you may not be familiar with, but there really is no other way to explain this concept. So I'll try and walk us through it. So we're going to talk about specifically, and today we're going to talk about columns with pinned ends. Okay, columns with pinned ends. So if you remember, when we were doing beam deflection, we had this basic equation, EI V double prime is equal to M. Now, if you notice, if you look at a column, it's just a beam kind of stood up on its end. So you would expect that this differential equation would apply in the context of column buckling, and I'm going to show you how it does. With a slight variation. Okay, so we have length L, and then we deflect into some deformed configuration, right, like this. Okay. Okay, now let's do similar to what we did last time. Let's go ahead and create a free body diagram and cut through the beam, or the column. So it's going to look, even though my drawing is really bad, it looks something like this, where we have a moment and then a load P that we have to solve for. We have some deflection V and some distance X. Okay, so this really looks a lot like beams, doesn't it? Even though it's columns. So what we're going to do is just use statics to essentially kind of replace M. We want to replace M with something that depends on the deflection, and that depends on the load P. Okay, so if we sum the moments now about A, set them equal to 0, we have that M plus PV is equal to 0. So obviously M is equal to the negative of the load P times the deflection V. And now we can plug in, we have our equation from beam bending. We can plug this in for M and rearrange, giving us the classic differential equation for column buckling. Okay, so this is called a differential equation. It's a little more complicated than any differential equation that we've seen so far, because it depends on V by itself as well as the second derivative of V. So this is called an ordinary differential equation with constant coefficients. It's homogeneous because it's equal to 0. So if you've had any of your undergraduate differential equation courses yet, you should recognize this as the very first equation that you probably studied. And so we want to solve for V such that we understand something about the applied loads that produce solutions to this equation. So let's go ahead and clean this up just slightly by dividing through by EI. Okay, so we're going to divide through by EI, so that goes to 1. And then we're going to set k squared equal to that constant P over EI. Okay, so this is called a homogeneous second-order differential equation with constant coefficients, and you can just look up its solution analytically. Little v is going to be written as some unknown constant C1 times sine of kx plus some unknown constant C2 cosine of kx. Okay, so now these, just like before, we're going to have to solve for these unknown coefficients by looking at the pinned connections. And then we'll have our final solution. Okay, so if we know that the deflection at 0 is equal to the deflection at the top, which is equal to 0 because it's pinned on both top and bottom. So if you plug that into the differential equation, you'll notice that v at 0 equals 0, which equals C2. So C2 has to be 0. And then the second condition, v at L, has to be equal to 0, which means that C1 sine of KL has to be equal to 0. We can't let C1 be equal to 0 because if C1 and C2 are both equal to 0, then that's not interesting. That's called a trivial solution. So if C1 is not equal to 0, we need to understand something about when the sine function is equal to 0. So this implies that sine, we have to find all the places where sine of KL is equal to 0. Okay, so we know that the sine function, right? We have a sine function. It just keeps going forever, right? And so it has an infinite number of locations where it's equal to 0. Okay, and we know that if KL is equal to n pi, n equal to 1, 2, etc. forever, then the sine function is equal to 0, right? So this is a condition now on our solution. Anytime that KL is equal to n pi, or k is equal to n pi over L, for all n greater than 0, we're going to have a solution to our problem. Remember, we set k is just that constant that we had. It was p over EI. That was k squared. So if we square both sides, right, let's go ahead and square both sides of this, then that implies that p over EI is equal to n squared pi squared over L squared. And then we can multiply through by EI. And so P, if the value of the applied load is equal to n squared pi squared EI over L squared, for any n greater than 0, you're going to have a solution to our differential equation. So in other words, there's an infinite number of solutions to our differential equation, is what this is saying. So we have P, let's just write this up again, P is equal to n squared pi squared EI over L squared for n equal to 1, 2, 3, and so on. And so that means that our final solution, V, our deflection, is going to be equal to C1 sine of n pi x over L. Okay, so this is an interesting situation where essentially you have an infinite number of solutions, right? So one solution might be, a sine wave that looks like that, okay? Another solution might be a sine wave with higher frequency, right? And so on, higher and higher frequency, right? So, okay, all of these are solutions to our problem. And the most basic solution would be something like that. Half of a sine wave, right? Half of a sine wave. Okay, so we're going to call these guys up here critical loads. So these are the loads that generate solutions to our differential equation. Okay. And we know if we apply a load of this magnitude, we know what the shape of the deflected column will look like because we have the solution. Okay, sometimes these are called mode shapes. They're sometimes called mode shapes. And notice that if there's an infinite number of solutions, but we're probably most interested for the solution when n is equal to 1. Because that means if you're thinking about it in terms of a column, the first critical load is going to buckle the column. So if the column is buckled, you don't really care about any of the higher ends, right? You don't care about frequencies any higher than the first frequency because the column has already destabilized and needs to be fixed or replaced. And so in civil engineering structures, if you're a mechanical engineer, you're actually going to be using equations like this to understand the frequency spectra for like airplanes or rotary components, and you'll need to understand more higher and higher frequencies. But for civil engineering structures like columns, we tend to only be interested in the lowest mode. Let's call this the critical load, which really just means n equal to 1. Okay, so in that case, P critical is just pi squared EI over L squared. Okay, so anything less than this load, you're going to be stable. Okay, you'll have a stable configuration. Anything greater than this load, and you're going to be unstable, meaning that it could all of a sudden the column could buckle or snap into a different configuration. And since this is just a simple column, if we want to understand the critical stress, so the critical stress, right? This is just a one-dimensional uniaxial member. So the critical stress is nothing more than P critical over the cross-sectional area of the column. So very simple. Okay, so let's do one problem to kind of cement these ideas. Let's say we have a column with pin supports P, and let's say it has additional constraints at the halfway point. Okay, so this is L 2L over 2. Okay. And so if you were to look at the cross section, let's say, of this column, it's going to be an I-beam. Okay. All right. So this flange here is what it's kind of like we're looking down on the top of this I-beam. Okay. So this I-beam is restrained from deflecting in this direction by these guys, but it can deflect out of the page also. So there's two axes of deflection. There's one in this direction, and there's one out of the page. And so if we have our I-beam, right, say it's a W200 by 34, we can go ahead and look up all the material properties. E is equal to 200 gigapascals. The kind of the plastic limit of stress, this is, we want to keep it below this number, is 300 megapascals. Okay, the length is 8 meters. And now we're going to have moments of inertia, right? We need two moments of inertia. We need a moment of inertia about this guy here, 1, 1 axis. And then we're going to need a moment of inertia about this axis too, the 2, 2 axis. So the I1 moment of inertia, the resistance to bending about this axis should be much larger, right, than the other axis, because that's how I-beams are designed. And so I2 is 178, so it's order of magnitude smaller. So in other words, it's bending in this direction. Doesn't have a whole lot of resistance to bending in this direction, but it does have a lot of resistance to bending out of the page, and that's why there's these additional supports at the midpoint to kind of make it more difficult for it to buckle. The cross-sectional area is 43.6 centimeters. And this is all in my notes if you want to review this problem more carefully. And so what we want to know is what's the critical load for this column, taking into consideration the fact that it can deflect in two planes. And so we want to find which load controls the behavior. So in other words, we're going to want to take the smaller load. All right, so if we've got, let's talk about the first case is buckling in the plane. So if we buckle in the plane, then we've got those additional constraints, right? So that's what we'll call that. Let's call this P critical 1 is equal to pi squared EI. And now the length, notice, is just L over 2 because of those additional supports at the midpoint, which gives us 4 pi squared EI, and this is I2. I2 over L squared, which is, if you plug everything in, it's 220 kilonewtons. Okay, so that's in the plane. Now, if we're out of plane, we have that the P critical 2 is just pi squared EI, let's see, 1 L squared, which is 830 kilonewtons. So obviously, even though you have twice the support, this one still controls because it's so much weaker in bending. in the plane. And so you would need to design the critical load for 220 kilonewtons. So the allowable load would be 220 kilonewtons. And then, so this would be the one that would control. And then if you wanted the critical stress, it would be just P critical 1 divided by the cross-sectional area, which in this case is 190 megapascals. So we're well below the plastic limit for this material.